Welcome. In this video I'm going to go through the last slides about ant colony optimization. In particular, the aspects we are going to view to speak about are other algorithms of ant colony optimization, how they should be combined with local search methods, how they can be applied to other problems, because you can recall that we have described the ant colony optimization algorithms when they are applied on the traveling salesman problem, but they for sure can be applied to other problems, other combinational problems. In fact, we will end these slides with two particular and very interesting problems, very interesting applications. In order to recap, you can recall that the idea of the ant colony optimization in algorithmic terms was that we at the beginning initialize the environment with a specific amount of pheromone for all the possibilities in the problem. In the case of the traveling salesman problem, you can recall that we got nodes and arcs which connect these nodes, and these arcs have some amount of pheromone. So at the beginning, this amount of pheromone is this value, and afterward we got the main loop where ants are situated in the first city, and they wander on the graph, constructing a circuit for the problem, which is done in this step. In this step, they are applying a transition rule where they decide the next city to visit according to the heuristic information for the different possibilities, and also the amount of pheromone for these possibilities. You can recall the formula, which was this one. Finally, after the ants have constructed their circuits, their solutions, these solutions are evaluated, and according to their fitness values, the arcs of these solutions receive an increase of pheromone. At the end, you return the best solution. That was the idea of ant colony optimization in this problem. We also described this simple case where I commented how one ant, this is just one ant, was constructing its circuit. The same for the second ant, the same for the third ant, and at the end, these 6 ants have constructed these solutions. These solutions have been evaluated, and according to these fitness values, they provide a contribution, a pheromone contribution to the arcs that are in these solutions. So this contribution is laid on the arc 1, 2, and also on the arc 2, 3, 3, 5, and so on. And the same happens for the other ants. That was the basic ant colony optimization algorithm, but researchers have proposed other variants of ant colony optimization algorithms. For instance, a very simple idea of an ant colony optimization algorithm is the elitist ant system. This algorithm is exactly the same as the previous one, the ant system, but when the pheromone is updated, the arcs that belong to the best ever solution receive an extra contribution of pheromone. The researchers came up with this idea because they noticed that the best ever solution might not be generated in every generation. So it might happen that in one generation there is an ant that generates the best ever solution, but afterwards there are several generations when there is no ant which generates that solution. So in that case, that the arcs of these solution would not receive any pheromone contribution. So they came up with this version, and obviously this algorithm provides a higher intensification, so it promotes a quicker convergence. Well, this is a very simple variant, and to my opinion, a more interesting variant is this one, the ant colony system. Well, the ant colony system introduces these three elements. Or instead, it uses these three elements. And the particular interest is this one. This is quite new. The previous ones, you already know how they work. Well, for the first one, the transition rule, the idea is that the ants are more intensifying, a bit more intensifying, because instead of probabilistically selecting one of the choices, one of the possibilities, according to a parameter, which is this one, according to this parameter, they select the best option. Nothing about a probabilistic option, a probabilistic choice, but just this decision. This decision is really probabilistic, but after this random decision, the election, the choice is not stochastic. They choose the best option. Otherwise, they select exactly equal to the previous algorithm, the AND system. So in this case, they are really applying a probabilistic and stochastic decision. Stochastic and heuristic decision. For the rest, the algorithm in this stage is the same. The second element is the global pheromone update. The idea is that here in this algorithm, not all the new solutions are allowed to provide contributions to the arcs, but instead just the best ever solution. Only the best ever solution. So only the arcs that belong to the best ever solution modifies have their pheromone amounts modified. The other arcs have their pheromone amounts intact according to this global pheromone update. And finally, the local pheromone update is this one, where every time an ant chooses an arc, traverses an arc, it applies this local pheromone update. And here you can observe that this equation says that the new pheromone amount is the previous one with some factor according to the evaporation and this contribution. But this contribution depends on the initial pheromone amount, which is a minimal quantity of pheromone. So actually this equation always reduces the pheromone amount on this arc. So the result is that every time an ant chooses an arc, the pheromone amount of this arc is reduced. The goal is to make following ants to choose other arcs. So this strategy clearly favors exploration. So it is because it is making ants to select different arcs. At the end of the current generation, only the best solution is going to receive a pheromone contribution. The rest of the arcs remain the same if we did not consider this reduction. But the effect is that those that have been visited observe their pheromone amounts reduced, and those arcs that belong to the best solution receive more pheromone. So this way, this algorithm is kind of providing a kind of balance between diversification and intensification, and this strategy is obviously for intensification, whereas this local pheromone update is for diversification. Well, the pseudocode of this variant of ant colony optimization is this one. The only difference with regard to the previous pseudocode is that every time an ant applies the transition rule to make the following decision, it also applies the local pheromone update. The rest of the code is almost the same, because at the end, when these ants have produced their solutions, then the solutions are evaluated and the best one, the global pheromone update is applied. And in this case, the global pheromone update only considers the best ever solution. There should be this symbol in order to close the main loop. Well, as I mentioned earlier, people usually combine ant colony optimization algorithms with local search methods. The idea is that after ants have produced their solutions, then they undergo local search optimization. You can apply local search to all these solutions or just some of them. Well, in case the local search optimization were expensive, computationally expensive, then you can reduce the cost by considering candidate list. I think that I have told you about candidate list, but in any case, the idea is that you do not evaluate all the neighbors of the current solution, but just a sample of them, which you have generated somehow. Yes. I told you about candidate list in taboo search. Perhaps, in taboo search. Perhaps you can recall that taboo search might be a bit slow, a bit computationally expensive, because it has to evaluate the whole neighborhood of the current solution. So in order to reduce this cost, you can reduce the number of neighbors you evaluate. Well, if you applied this combination of ant colony optimization and local search, you can also optimize the fitness function of when you evaluate the neighbors. I have also told you about this optimization. And something which is very interesting is that if you make this combination, ant colony optimization with local search method, then you are using ants to construct probabilistically initial solutions for the local search. Well, this construction, which is probabilistically, which is stochastic, probabilistical, obviously uses the pheromone amounts you have deposited on the graph. But since you are using since you are using ants to generate initial solutions, and afterwards you are applying local search, then ant colony optimization are similar to multi-star local search algorithms, and in particular they can be similar to GRASP. You can recall that GRASP generates heuristically but random greedy initial solutions which afterwards undergo local optimization. So here the effect is almost the same. The difference is that ant colony optimization applies a memory structure, which is the pheromone matrix, the pheromone information, for generating the following solutions. Whereas GRASP do not use typically memory structures. Well, so the general ant colony optimization framework. The fact is that after the initial proposals of ant colony optimizations, there were different researchers applying ant colony optimization to other problems, not just the traveling salesman problem, other combinational problems. So these authors, which are the originals, of the ant colony optimization, decided to provide a general framework for applying ant colony optimization algorithms to other problems. Well, the idea is that you have to adapt the components of the algorithms, which are the transition rule and the pheromone update, mostly these two components, to the addressed problem. The basic idea is that in order to apply ant colony optimization algorithm, you have to represent your problem as a weighted graph. Your problem has to be represented this way, as a weighted graph, where there are arcs, and these arcs can tell the ants the heuristic preference they have, and they can also store the pheromone amounts they receive. So this way, the idea is that every ant colony optimization algorithm should be able to use heuristic information and memoristic information, and you are doing that if you represent your problem as a weighted graph. Well, the pseudocode would be mostly equal to the previous ones, where your ants applies the transition rule to generate the different solutions. Afterwards, the pheromone matrix or the pheromone traces amounts are updated, and afterwards you could consider the application of some optional actions. These optional actions can be, for instance, the application of the local search, local optimization of the previous solution. Just in order to provide you with an example, let's suppose that you would like to address the NAP/SAP problem with ant colony optimization. So in that case, your solution would be something like this. How can you make ants produce solutions like this one? Well, a very simple idea is to make the ant go over the positions of this vector. So at the beginning, the vector is kind of empty, and at each step you got two possibilities, either setting a 0 or a 1 in this decision variable. So this is actually an arc of your graph. You got an heuristic information for this choice, but also a pheromone amount for each of these two choices. You evaluate these two possibilities, and according to the transition rule, you set this value. Afterwards, the ant moves to the next position, where you got again two possibilities, and so on and so on. Well, here the heuristic information might be, for instance, the heuristic information of the NAP/SAP problem for setting this decision variable to a 0 or a 1, or so on. Well, in case the NAP/SAP is empty the heuristic information would always choose the one value. But instead, you can make this wandering of the AND, you can draw a permutation, so the wandering of the AND can be follow a different order. And this way, the heuristic information is not always returning or promoting the selection of the value 1. And the pheromone amount is always the amount you lay on these options. So for instance, let's suppose that in this case you got 2 options, but you got more pheromone for the option 0 than for the option 1. So this way you are making more probable to set this decision variable equal to 0. Well, finally, some applications of some interesting, or at least to my opinion, interesting applications of ant colony optimization. Well, the first one is AntNet, which is applied on packet routing in telecommunications. So the idea is that you got a network, a computer, well, whichever kind of network. In particular, in this experiment, is a computer network where these nodes are computers, and I don't know if you know how the internet, how computer networks are configured, but the idea is that each of these nodes have got routing tables. So these tables let these nodes decide where the data packets should be transmitted to. So for instance, let's suppose that this computer would like to communicate with this one. So this computer has got a routing table which tells it that in order to reach this computer, it should send the data packet through this link. This computer has also got another routing table, and it received the packet, and the routing table tells it to send the data packet through this link. This computer has another routing table, the data packet is sent through this link, and so on. Well, in any case, you can observe that this is not the only path for sending the packet from this origin to this destination. So there are different solutions for this particular data packet. Obviously, in this computer network, there is not only just one data packet traveling. There are a lot of data packets, and ideally, you got your network configured according to the routing tables in order to send the data packets to their destinations, and not losing any of these data packets, and making these data packets reach their destinations in a short period of time. Well, so there were some researchers that considers ant colony optimization for updating the routing tables. So the idea is that In this network, there are two types of packets. There are two types of packets. The data packets I commented previously, but there are also some routing packets. And actually, these routing packets are kind of ants, which are wandering on the network. All the nodes, all the computers at some frequency generate ants with particular destinations, and these ants wander through the network according to some information of the networks, which is some heuristic information, which is perhaps the bandwidths or transmission delays of the links, but also some memoristic information, some pheromone information, which is stored in the routing packets. So the ants apply the transition rules, deciding which nodes, which links they should choose. Afterwards, when they reach their destination, the idea is that they come back the same way they have used to reach their destination, but they update the routing tables. If they have lost too much time, then the new values of the routing tables would be reduced. But if they have found interesting routes, interesting paths, then the routing tables will observe the pheromone amounts increase. Well, one of the results, of the interesting results that these researchers observed, was that the algorithm was able to produce the best results against other algorithms, but also it was able to adapt to network changes. For instance, you can think of that computers do not work forever, so some of the computers in the network might get down. If this is the computer that has been shut down, then in order to reach this destination, you have to follow another path. So ants can notice these changes in the computer network and can update the routing tables to automatically to make the whole network still work. Well, this is the first application, and the second one is for logistics. So in this case, they apply algorithm optimization for designing the routing plans of different vehicles. So in this problem, let's suppose that you are the CEO of a company where the company has got different vehicles fleets, and you are to deliver some goods to your clients. For instance, let's suppose that your clients are different supermarkets in a region of a country. So this is a very simple case. Let's suppose that here you got a depot where your trucks, your vehicles load the goods, go to the assigned clients. This is the plan for one vehicle, this is the plan for another vehicle, and so on. Well, in this case this is very simple, but actually they have applied in this case they have applied this algorithm, which they called ant optima, to a large company which delivers goods to the whole Italy. In particular, they delivered goods to 600 supermarkets. They got 200 vehicles with different capacities. Some of the goods that they have to deliver should reach their destination in less than a given time. For instance, let's suppose that these goods are perishable goods, such as, for instance, that they need some refrigeration. For example, they could be milk or something like that. So in the experiment they applied their algorithm was able to provide plans for their trucks, their vehicles, with 52 pallets of goods to 6,800 clients for 20 days, and this plan was designed in less than 5 minutes. Previous to this algorithm, this company applied human experts, in order to design these plans. And these experts usually needed several hours in order to design these plans. But in addition, the plans of the algorithm were usually much better than those provided by the human experts. Here you can observe some of the results. So, for instance, in the expert plan, the number of routes for the vehicles is 2000, but these are two versions of the ant colony optimization, and here in this case they use less tours, less vehicles than the plan of the human experts. This also means less kilometers. And this was accomplished thanks to an increased loading of the trucks. So the algorithm was able to load the trucks much more than the plans of the human experts. So you can notice that this is a huge save of money for the company. Well, There are for sure a lot of other applications of ant colony optimization as any other meta-heuristics. Some final comments about ant colony optimization is that they are easy to be applied to different problems. In all these cases, you have to translate your problem. You have to describe your problem as a weighted graph. In this stage, you have to provide a definition for the pheromone tracks. You have to tell the algorithm what the pheromone tracks mean. If you provide a bad translation, a bad interpretation, then it probably your algorithm is not would not provide you with good solution, or at least interesting solution for your problem. If you are able to provide a adequate interpretation of the pheromone tracks, then it is probable that you obtain better results or more interesting results. In any case, the ant colony optimization should be balanced and provide a good trade-off between exploration and exploitation, or diversification and intensification. And you know that there are some components for exploitation or intensification, which are these ones. For instance, laying more pheromone on the best solutions. This is for intensification. And there are other components for diversification, such as these ones. Well, we have not commented all these alternatives, but there are some proposals that apply these ideas. For instance, there is a proposal that applies a kind of mutation operator on the pheromone matrix. It is very usual to combine ant colony optimization with local optimization. And in contrast to other algorithms, in contrast to GRASP, ant colony optimization applies memoristic information. But in addition to this memoristic information, ant colony optimization has been designed to exploit problem knowledge, which comes in the form of an heuristic information source, heuristic information. This is obviously for intensification, but usually this heuristic information helps the algorithm converge faster to good solutions, and you can balance this convergence with other components. The heuristic information is not helpful in all the problems. There are some problems such as this one I have not commented to you, but in this case, introducing some kind of heuristic information is not helpful. In any case, you can apply ant colony optimization without any kind of heuristic information. Sorry, this is in Spanish, but it is not too much interesting. Finally, there is a question which is the most appropriate number of ants in the algorithm, or in particular, can you wonder what is the benefit of using a colony? This means a set of ants instead of just one ant. because you can apply it one ant always, getting out of the ant hill, making a wandering and going back to the ant hill, and you can repeat that through many iterations. After each iteration, the pheromone amounts are updated. So what is the difference between using just one ant and a set of ants? I will leave this question for you. Well, and that's all. These are some bibliography for ant colony optimization, and that's all of these kind of algorithms. I hope that you have liked them. See you.